So I have an equation here, and I'd like to see if we can use Newton's method to approximate its solutions out to 10 to the negative fourth. In other words, I want to be sure that the first four decimal places of my answer are correct, right? That they match the exact value. So Newton's method really doesn't talk about equations. Newton's method operates on functions. So the first thing I need to do is I need to get a function that I can work with. And the function is just going to be equal to that polynomial. Right? So saying find the solution to that equation is the same as saying find a root of this function. Okay, so first, again, just get the formalities out of the way. This is clearly a C2 function. Its first and second derivatives are continuous. And the first derivative is 3x squared plus 3. That is always positive. So it doesn't matter what number I choose for my first approximation or what numbers we come up with for the later approximations, they are never going to make that derivative equal to 0. So we've met all of those requirements here. So it's pretty easy to see. If you evaluate this at -1, you get -1. And if you evaluate the function at 0, you get 3. So the intermediate value tells us right off the top that there is going to be a root somewhere between -1 and 0. So for lack of any better choice, I'm just going to kind of do the obvious. I'm going to split the difference. I'm going to go with P0 equals -0.5 as my first approximation. All right, so now we need to go to the formula, right? Remember the formula for Newton's method is this thing. And I'm just going to take my function, put it into the numerator there for f of p sub n. The derivative, that's what I talked about a minute ago, is 3x squared plus 3. So if we substitute those two expressions in there, the formula becomes this. All right, so now it's really just calculator work or Excel or whatever program you like to use to do these repeated calculations. And if we do that, right, I'm going to put -0.5 into the right-hand side of the formula here, and that's going to give me P1 is equal to -0.86667. That becomes the new P sub n. You keep doing this iteratively, and you see it only takes 3 sets of calculations before we've narrowed this down to the point where the first 4 decimal digits have stopped changing. All right, so based on this, I would say that the answer is -0.8177. Now, if you've been following along with the lectures, you remember we looked at this equation already. Right? We looked at this back when we were first started talking about iterative methods, and we approached it through 3 different ways. We came up with 3 different functions, all of which had a fixed point that matched this solution. One of those functions just straight up diverged. The other one converged to the answer, but it did it really slowly. And the third one did it relatively quickly, but even that one, I've got the results here for you to look at. Even that one took, 1, 2, 3, 4, 5, 6, 7, 8, 9. Even this one took 9 evaluations before we finally got out to the level of accuracy that we needed. So hopefully you're already starting to get a feel for why Newton's method is such a really awesome tool, right? We can get results very quickly from it with a relatively small number of calculations. So the next example, we're looking at something a little different. We're looking at a question where you aren't given a function, you aren't even given an equation. You have to come up with an equation. So the question is going to be find an approximation of the fourth root of 6. And we can use Newton's method to do that. We're just going to have to first come up with an equation that has that number as its solution. Then we'll be able to apply the method and come up with a result. So if you'd like to see the full context, you can click on the upper link over here to the left. That'll take you to the corresponding lecture. The link below will take you to the video that I was just describing. And if you like this, please don't forget to click on the like button down below.